You'll want your formula sheet out for this, not because any of the formulas we're going to be using are complicated, they're not, but because there's something on your formula sheet that is related to these questions. I call this Conservation of Linear Momentum Part 2. We're going to continue to solve problems that involve linear collisions. But the problems we're solving involve two physics principles being used. Now, when you write your diploma exam, which is a long ways away, the final two questions of the diploma exam will be two numerical response questions. And the first numerical response question in that pair will be a calculation question that Alberta Ed even admits are extremely difficult problems. Alberta Ed has openly said, we expect less than 40% of the province to be able to get the right numerical answer to that question. They're very difficult. And it will always be a calculation that involves multiple steps and two physics principles. I'll get to that in a second. And then the next question in that numerical response pair, the very final question, will always be the same. When you calculated the answer to the previous question, you had to use two physics principles. What were they, and in what order did you use them? How many of you from Physics 20 remember doing that? Okay. Probably with projectile motion would be one of the only cases where that would happen. Because when you do a calculation regarding projectile motion for an object, when you do a calculation regarding the horizontal motion, which is uniform, it's physics principle 0 on your formula sheet. Right. We're looking on our formula sheet. If I can jump ahead here, we're looking on our formula sheet at the physics principles. When you do that calculation for the horizontal motion and you use speed equals distance over time, you're using the concept of uniform motion. And then wherever in those projectile motion problems you use kinematics with acceleration, like, I don't know, d equals VIT plus a half AT squared, then you're using accelerated motion, which is physics principle 1. By the way, and I don't know if, I know I did this with my Physics 20s. Your Physics 20, if you didn't have me, your teacher might not have. Physics principle 1 and 2 are both accelerated motion. They're just different types of acceleration. It drives me nuts that it kind of implies that 1 is accelerated motion and then it doesn't say 2 is accelerated motion. They're both accelerated. 1 is linear acceleration, 2 is centripetal acceleration. We'll get to that though. The bottom line is when you did those projectile motion problems, sometimes you had to do a speed equals distance over time calculation first and then do a d equals a half AT squared calculation, in which case the two physics principles you would use and the order in which you're using them would be 0, 1. You remember that, I hope. Okay. So this year what's going to happen is, because we're going to finish everything on the formula sheet, we're going to learn everything in the textbook, we're going to complete your high school physics education, there are going to be dozens and dozens of these problems. Like sometimes the answer to the question will be 7, 1. Because this difficult problem you're asked to do involves using conservation of charge and then accelerated motion. Sometimes it's going to be 3, 2. Sometimes it will be 2, 3. So we have to reacquaint ourselves with these physics principles and also apply them to new situations. That's what we're doing. Here's the first example. This is called a ballistic pendulum. I do have a little model of a ballistic pendulum. I'm not going to show it to you right now. Maybe tomorrow or next week when we're reviewing, we'll do a quick experiment with it. It just fires a ball bearing into a block, and in the center of the block there's kind of a rubber hole, and the ball bearing sticks in there. The idea is, and I'm going to refer to the diagram on the screen right now, is that when that bullet hits this block of wood, and this is literally how you can find the speed of a bullet, it enters the block of wood, it embeds itself in the block of wood, and then the block of wood swings up. And the bullet is moving very, very, very fast, right? Obviously, it's a bullet. When it hits the block of wood doesn't move very fast because it's much more massive. We used to do this. When I first started teaching physics, I would bring in a little pellet gun, and we would hang a block of wood from the ceiling, and we would do this. And then we would look at the rating on the pellet gun, and we'd compare the speed we get for the bullet with the rating, and it's very close. Of course, you can't bring a gun to school anymore, not even a pellet gun. Okay? So we have to talk about it, and I'll show you that model next week. Would you agree, just forgetting about actually calculating anything, that the faster the bullet is moving, the higher the block will swing? I hope you would understand that the universe is not rolling dice all the time. That if I fire a bullet with a certain speed into a particular block of wood today and it rises 10 centimeters, tomorrow it's not going to rise 20 or 5 or 3. And what I'm getting at is there must be a relationship between the speed of the bullet and the height. These two things are physically connected somehow. They're connected with physics. And the goal in this first question is, if we know the speed of the bullet, what would the height be? Now, that is not how a ballistic pendulum is used. A ballistic pendulum is used where you measure the height to calculate the speed, right? If you knew the speed, you wouldn't need this. But it's easier for you to understand what's going on if we do this problem first. Okay? Then we'll work on the other problem. So there are two things happening here. When the bullet embeds itself into the wood, there is a collision. And this is what I talked about yesterday with friction. Is there friction between the bullet and the block of wood? Yes, but that's the force that they're exerting on each other. That's not going to make this a non-isolated system. Outside forces of friction are negligible. The friction between the air and the block of wood is negligible. The friction between all of the moving parts is negligible. And what I'm getting at is this collision occurs in an isolated system. And if it occurs in an isolated system, what this means is momentum is conserved. Okay? So during the collision, and you have to listen carefully to the words here because this is a slippery idea. From the time that the bullet starts touching the wood until the time that the bullet stops moving relative to the wood, the whole thing is going to start moving initially. But as soon as we get that bullet being stopped in the wood, that's what we're talking about when we say final. So the I here the I in this refers to the momentum of the bullet before it hits the wood. The F refers to the bullet in the block immediately after the collision. You with me? So if you knew the speed of the bullet and the mass of the bullet and the mass of the block, you could find the speed that they will both have afterwards. From yesterday, what you would do, and you are going to write this down, is you would say that mv of the bullet before must equal mv of the bullet and the block after. Are you with me on that? Okay. I'm just curious, side note, doesn't really matter. How many of you see that direction really isn't important in this question? Because everything's moving to the right, so who cares? So I could just say mv equals mv without the vectors. Okay. Let's just walk away from that for a second. There's something else that's going on. Immediately after the bullet stops moving relative to the wood, that whole bullet block is going to swing up. But that means it's not a collision here. What we've got, maybe I should explain this. This diagram on the left shows 2 points in time. It shows the bullet outside, and then if you want, you can add the bullet inside. There's the before, there's the after, right? Over here, there is also a before and after. There's the bullet in the block of wood when it's still at the bottom, and then at the maximum height. And where I've drawn it is the maximum height. It's not going higher, okay? This is not a collision. This is a pendular action. It's a pendulum. And whenever a pendulum swings around, and if you were in my class, remember we had that big long pendulum here, and if you were in other people's classes, I'm sure you did stuff with pendula. When that pendulum is at the lowest point, it's moving as fast as it will in its action if we allow it to swing back and forth. When it's at its lowest point, it's moving fast, and as it rises, it loses speed until at the very top it stops. But we don't want to talk about losing speed. We want to talk about losing kinetic energy. And what's happening here is energy. This has nothing to do with what we talked about yesterday. This is physics 20. Energy is conserved. At the bottom of this swing, this block of wood and the bullet has only kinetic energy. It has only kinetic energy because I am saying that's the lowest point. I'm not going to calculate gravitational potential energy relative to the floor. I don't care. And then at the top, there is gravitational potential energy. And in physics 20, nobody really worries about saying gravitational. You just say potential. But in physics 30, we are going to learn about electrical potential energy and magnetic potential energy and nuclear potential energy. So energy is conserved here, which means that during the swing, EK at the bottom equals EP, gravitationally speaking, at the top. Now, we'll get to the calculations in a second, but what I need you to understand is on the left-hand side of the screen, we've got an equal sign. The two masses on both sides of the equal sign are different masses. We're talking over here about using the mass of the bullet, but over here about using mass of both. With the energy formula, it's the mass of both at the bottom and the mass of both at the top. So where do we proceed from here in terms of an analysis? We say for this physics principle of conservation of energy, 1/2 mv squared will equal to mgh. I would say to you that these problems, sometimes they are complicated no matter what, but these problems are easier if you approach them through an understanding of the physics principles. Alberta Ed says, and I agree, students who strictly speaking want to memorize a formula to answer a problem are going to be nowhere as successful as those students who understand the physics principle that creates the formula. Finally, we're almost ready to grab our calculator, and I'm not going to be writing a lot down here in some of these. Finally, you need to understand that the final speed that the bullet and the block have after the collision is the initial speed that the bullet and the block have in their pendular swing. We can also, before we go on, recognize that I am allowed to do this. You don't have to do that. You can put the masses in. But since that mass on the right-hand side of the screen, on both sides of the equation, is the mass of the bullet and the block, they're the same, so you can divide both sides by that. Now, let's take a look at the big picture here, everybody. The big picture is we want to know the height? That's the question. So we're approaching this from a logical standpoint. When you look at what we want to know, on the right-hand side of the screen, you need to know the value of G, which is 9.81 newtons per kilogram, or 9.81 meters per second squared. We know that. But you also need to know V, the V I've highlighted in blue on the right. Well, but we don't. But that's okay. On the left-hand side of the screen, we can use conservation of momentum to find the speed they both have, so that we can then use conservation of energy to find the height that they will both reach. And it's not a simple question. Well, I think it is once you understand it. So what are we going to do here? Well, we're going to put in the numbers. And I need to look at this. I've forgotten the numbers. 14.5 and 2 kilograms. So what you would put, I will show my substitution here, is 0.0145 kilograms times the 640. Thank you, Craig. And again, I know there are teachers in the province that would look at what I'm doing. Oh, he's not putting units. That's just me, okay? I think they get in the way of you understanding physics. Use the proper units, but you don't need to write them in for this question. And then here we're going to have 2.0145 times V. Craig, I'm just going to ask you, why 2.145? Where did that come from?
That's the block and the bullet.
Right, that's the two masses added together. Oh, okay, calculate that for me, please. Take your calculator and figure out what we get for V. So we're taking the mass of the bullet times the speed of the bullet, which will be the momentum of the bullet. We're dividing by the mass of both, because that momentum of the bullet is the momentum of both. So to find the speed of both, we divide by the mass. And I get 4.6 meters per second. I'm going to write 4.6 down, but I'm going to carry all of my decimals in the next step. Personally, I'm really not a fan of having that half here. Before I cancel the m's, whoops. Before I cancel the m's, what I probably would have done is multiplied both sides of this equation by 2 and get mv squared equals 2gh. I'm just canceling the half. Then I would cancel, 2mgh. I'm one step ahead of myself. Listen, I don't care where you cancel the m's. You could have canceled them to begin with or afterwards. That's a little grade 9 math thing. And then I end up with v squared equals 2gh. So I have to, let me show the substitution here. I have the 4.6 squared equals 2 times 9.81 times h. I feel as though I shouldn't need to explain this, but I'm going to. Would you agree, looking at that equation, I need to take v squared and divide by 2g? Would you agree? Okay, and that's true. But I hope everybody sees, let me get my answer here. This is my v squared. This is absolutely incorrect. Because what I'm actually doing is dividing by 2 and then multiplying by 9.81. You either need to put that 2 times 9.81 in brackets, or calculate it first, or if you know me as a teacher, I look at this and say, I have to take v squared and divide by 2, and I need to divide by g. That's what I do. Okay. Bottom line here, we end up with 1.08 meters. And that's the answer. That's the numerical answer to this question. The question was, what is the height reached by the pendulum? Oh. I don't know what that was. Felt like a bee sting, but I don't see a bee. They want their answer in centimeters, though, so it's 108. That's the numerical response answer to this. All right. Now, I spent an awful lot of time on that question. The next one, 3 and 4, is going to be really quick because it's the same question in reverse. What are the 2 physics principles you used, and in what order did you use them? Well, I hope it's clear that you used conservation of momentum and you used conservation of energy. It's just a matter now of you saying, well, which one did I apply first? Do not look at this question and go, well, the collision happens first, so that's why we use momentum. Doesn't matter the order in which reality happened, it's the order in which you did things. Now, it does turn out that we did do a calculation here first, under momentum, right? So we used conservation of momentum first, and then we used conservation of energy. So the answer to this numerical response would be 4 and 5, 4, 5. Okay. Let's try one more. Same scenario. I'm not going to go through the big explanation again. Okay. We know that during the collision, mv will equal mv. This will be of the bullet before, this will be of both after. We have already learned and reasoned out that during the swing, the kinetic energy of both at the bottom will be equal to the gravitational potential energy of both at the top. The difference here is, this is a question that's a more realistic question. You don't use a ballistic pendulum to predict the height that something's going to go at. You measure the height to find the speed. So we are after the speed of the bullet. Okay. Well, do you know the mass of the bullet? Yes. Do you know the mass of both? Yes. Do you know the speed of both after the collision? No, you don't. That's the clog in the pipe. That's the thing that's preventing us from getting to the finish line here. But should recognize, better use a different color. You should recognize that if we want to find that speed that I've highlighted in yellow, it's the same as this speed over here. And I think literally once you see what's going on here, the time it takes you to calculate the answer is a minute or two. Right? I'm not going to, in this particular example, I guess I will. I feel as though I shouldn't need to write down the numbers, but I will. So the mass of the bullet is 0.012 times the speed, which we're after. This is equal to the mass of both, 2.312 times, well, this is what we need to find, right? So we go over here. I would say that making this leap mathematically, it's not even a leap. Multiply both sides by 2 and cancel the masses. V equals the square root of 2 times g times the height. And everybody should know what g is. I'm not going to write 9.81. Don't forget, all of your evaluation in this course, in exams, is multiple choice numerical response. Nobody cares about this stuff. If it's written response, you should write the stuff down. And that's an assignment, not an exam. So I'm going to calculate the speed that they both have by taking the square root of 2 times 9.81 multiplied by 0.085, 1.29 meters per second. It's very common for students to forget the square root thing, to see v squared equals 2gh, and they calculate 2gh and then they forget the square root. That's the speed that they both have afterwards. This is the speed, which goes here, and we're just, one set of calculations away from getting the answer. Are you guys with me on this? Okay. So now I need to take 2.312 multiplied by that answer. This number that you're looking at, oh, I'd better check. Is the sum of both masses 2.312? I wrote that down without even thinking too much. It is, okay. What you're looking at right now is the momentum that is in the system after the collision. But momentum is conserved, so this is the momentum that's in the system before the collision, which means it's the momentum of the bullet. So if we divide that by the mass of the bullet of 0.012, we get 249 meters per second. Oh, good. I like this question. Now, anybody else get 249? Okay. Let's look at the nature of this question. It says it's A point B times 10 to the C. So that means we have to take 249 meters per second and put it into standard scientific notation to 2 digits, A point B, which means it's going to be 2.5 times 10 to the 2 meters per second. So what we've got happening here is A is 2, B is 5, C is 2. The answer is 252. Okay. Now, what's going to happen is you're going to be doing work like this in some of the problems I've given you, and you will look in the back at the answer, and you will see the answer is 252. And your brain's going to say, I didn't get 252, I got 249. This is not 252 meters per second. It's 2.5 times 10 to the 2. Okay. What are the physics principles? Well, in this particular question, what we did first was a calculation on the right side of the screen. Whoops. There you go. We did this calculation first, which means we did a conservation of energy application, which I should know this, but is it 5? Physics principle 5 for energy? Okay. And then conservation of momentum, which is physics principle 4, we did second. So we would record 5, 4 in the boxes. Are you still with me here? Every now and then I look at a diploma exam and I see one of these questions and go, man, I never thought about that before. And then I include it in my lessons over time. When I said there's dozens of these, there are literally dozens that I've seen. You never know what it's going to be. I've never seen this one, but I made it up. All of the ones we're doing today, by the way, involve conservation of energy and conservation of momentum. What we have are two little cars. They're only 500 and 600 grams in total, each, rather. And the one at the top is released from rest. So I don't know if you can tell, but there's a bit of an angle I put in the diagram where it's pointing down a bit. So I'm just standing there, leaning over and holding this car, and I let go, and it goes from rest. And what's going to happen as the car rolls down the hill, before it touches car 2, what's going to happen is it's going to accelerate. And the reason it's going to accelerate is because from the point where the front of the car is here to the point where the front of the car is here, but just getting ready to slam into car 2, energy is conserved. But it's the opposite of the pendulum. It's not kinetic energy being lost and turning into potential. It's potential energy being lost and turning into kinetic. So as it goes from point A to point B, from A to B, we have energy conserved. At the top, we have gravitational potential energy of car 1. And at the bottom, we have kinetic energy of car car 1. Now what happens is the following. Car 1 connects with car 2, and they move off together. You know, I am totally in teaching mode right now. What I draw is not necessarily what you can draw. I just want to demonstrate something to you visually. If I were to say that this is car 1 and this is car 2, then car 1 ends up being here at some instant in time, just getting ready to plow into car 2. But once it does make contact, there will be a collision. And these two cars are going to move off together. And if I talk about, I'm going to put this dot back. I don't know why I erased it. If I talk about point B and point C, from B to C, there's a collision, so momentum is conserved. Whatever the momentum of car 1 has just when it reaches the bottom, but just before it hits the second car, whatever momentum that has, that will be the momentum of both cars. You'll notice as we get a little bit deeper into this, I'm not too worried about subscripts or vector symbols or stuff like that. We're trying to understand the physics, not the notation right now. I think the notation will just get in the way. You know, I haven't put a lot of subscripts over here, but what do we know about this mass on the MGH? Paige, what is the value of this mass on the MGH? The first car. And what about this m and the 1/2 mv squared? It's still the first car because that's point B where it's just getting ready to touch car 2. In these problems, whenever you have that pendular motion, it will always be that the masses are the same. However, Alex, what is the mass on the left side of the momentum equation?
That's both. That's the sum of the two cars.
Nope, it's not. The only thing that has momentum before the collision is car 1. We're still talking here about this point right here. So this is only 0.5 kilograms, but the mass at point C is both. Okay, we kind of set this up. I don't think I need to write that A to B is conservation of energy, B to C is conservation of momentum. We know that. Let's look at it logically now. What are we trying to find? I mean, I started explaining this before I even got to this. Let's actually go to number 6. Usually they ask you for the calculation first, but sometimes they might ask you for the principles first. Number 6 says, what's the speed that they both move off at? So we are after this. Do we know this mass right beside the V? Well, yeah, it's 1.1 kilograms. 500 grams plus 600 grams. Do we know the mass over here? It's 500. We're missing this speed, but I'm running out of colors. I'll use my god-awful, I hate this thing. This speed is the same as this speed, right? This is the speed of car 1, both at the bottom of its incline, at the bottom of its rolling, and it's also the speed before the collision. Once you set it up, again, it's pretty basic, except for one thing. What do I put for H? Charlie?
The 4.30 meters? Or, oh.
No.
Never mind.
I don't put 4.3. It's not the average, no. Alex?
Is it 2.8, the difference?
It's the difference. See, this is important. As soon as we say at point B that that first car has only kinetic energy, we're saying there's no potential energy there. We're saying that this portion right here, this location, vertically speaking, has no potential energy, which means that's H equals 0. So we have to find the difference between 4.3 and 1.5, and Alex has done that, and it's 2.8. So you're going to put 2.8 here. Equals 1/2. I didn't get rid of the half this time, but who cares? Take 9.81 times 2.8 times 2, and then we take the square root to find the speed. Again, I kind of go under the assumption here that, wow, geez, you would never show that rearranging. I mean, you're not going to write down, you could, but there's no need to write anything else down other than the speed. So 2 times 2.8. I don't distrust you, Alex, but can somebody else confirm it's 2.8? Okay, good. Thank you, Gabrielle. I need to take, see, it's so easy to go just, 54 meters per second and move on. Got to take the square root. That would be pretty fast anyway. I think maybe your antenna would start moving around on that one. So the square root of the answer, we're getting about 7.41 meters per second. And again, not to be overly repetitive, but that is both the speed that car 1 has at the bottom just before it hits car 2, and it is also the speed that car 1 has just before it hits car 2, which means we can put it in here. So now I can put 0.5 kilograms, that's 500 grams, times that 7.41 equals 1.1 kilograms. That's the sum of the masses times V, which we're after. And again, as we go deeper and deeper into this, I don't feel the need to write a bunch of subscripts each time. .5 times our answer. I need to divide by 1.1. I think we probably want, I don't know how many digits we want.
It says 3.
It says 3? Thank you. So we want to record that to 3 digits, which would be 3.37. Again, the whole 2 physics principle deal is pretty easy today because it's always going to be 4 and 5 or 5 and 4. So we just have to look at this and say that we used conservation of energy first in calculating the speed, then we used conservation of momentum. So for this, it would be 5.4. Am I right? Did I get them in the right order? Okay. And this was 3.37. I have one more to go. And I just want to set it up and give you a few minutes to plug around on your calculator and get the answer. I will set it up for you. Exact same scenario? Really, it is. I'm not lying. It's the same scenario. The difference is this time you are told the speed they move off together at, and you have to work backwards to find the height in the diagram. So we still have, mgh equals 1/2 mv squared. And I want to be very careful here. Does car 1 start from rest? Okay, because it doesn't have to. You might see a problem in today's assignment where car 1 is already moving when it starts going down, in which case you would add another 1/2 mv squared to the left of this equation. This is your conservation of energy. Simplified, it's that, because I can multiply both sides by 2, and I can cancel the masses. my conservation of momentum is mv of car 1 at the bottom equals mv of them both after the collision. These masses are different and I can't cancel them. Would everybody agree that I need to find h? Okay. What's preventing me from finding h is I don't know the speed that car 1 has at the bottom of its rolling down the hill, but the speed that it has at the bottom of rolling down the hill is the speed that it has before the collision. So this speed is the same as this speed, and you know the mass of car 1, and you know the mass of them both, and you're told the speed of them both. So I'm asking you on your own to find the missing speed from conservation of momentum, to use it to find the answer to the question, and while you are doing that, if you need help, I will be writing down the numbers up here. So I'm getting for the speed with conservation of momentum on the right-hand side of our screen, I'm getting for a speed 5.673 repeating meters per second. That is the speed before the collision of car 1, which is the speed after the rolling of car 1. I need to square that, divided by 2, divided by 9.81. And I get for my h from my formula 1.64. I'm going to come back to that in a second, but I'm seeing nods. What are the two physics principles? This part becomes easy because there's only one limited case here, right? 4-5 or 5-4. This would be 4-5 because we did momentum first. And conservation of momentum is 4. Does anybody have any comments or questions about our supposed answer? Because it's not correct. That's wrong. We have not done anything wrong, but it is not the answer to the question. Gabrielle?
Do we have to add 1.2?
Absolutely. We're back to this idea that as soon as we say mgh equals 1/2 mv squared, you're handcuffing yourself to the idea. It's a bad analogy because it makes it sound like it's a bad thing. But you are confining yourself to the reality that this means h equals 0. So what we've actually found when we got that 1.64 is we have determined that this is 1.64 meters. And, you know, the fact of the matter is, it's maybe more so in Math 30. These are highly academic courses. You're always going to be looking for little wrinkles or things that you haven't taken into account. So as Gabrielle said, the H in the diagram, which is what we're asked for, it says what is the height above the floor, and the floor is down here, would be 1.64 plus 1.2. That's going to be the answer you would need to record. Which is 1.8. 2 digits would be 1.8. There are a variety of questions here. It's 1 to 14, but what that is 7 problems. Because it's 1, 2, 1, 2, 1, 2. Each of these pairs, 1 and 2, 1 will be a question, 2 will be physics principles. 3, 4, same thing. Once you get into the groove with these, they're all the same, except this is the ballistic pendulum that we'll play around with a little next week. So this is on the left, a little, you pull that plunger back and there's a clip that holds it there, and then you put the BB or the bearing inside this chamber and you release it, and it goes into that block. And the block is going to hit this metal bar here, and it'll push the metal bar up, and the metal bar will stop there, and then you'll be able to use trigonometry to find the height. And we'll probably go through a calculation of that. There is one example here, one problem here rather, where, why I have all that? Oh, that's the lab. Where the bullet is going to have a collision with the wood and conservation of momentum will occur. This whole thing with the bullet in it will have kinetic energy, and the kinetic energy is going to reduce to 0, but not because it swings up. Where will the kinetic energy go? Yeah?
Into the spring.
Spring potential energy. So here you're going to have 1/2 mv squared plus or equals, from physics 20, do you happen to know the formula for spring potential energy? It's good that you're looking because you know it's got to be there.
1/2 kx squared.
1/2 kx squared, where k is the spring constant. So we did a number of labs with springs, right? You should be familiar with what x is. It's how much it compresses, and what k is.